Welcome back to the AIS-156 series. In this video, we're covering the mechanical shock test, another important mechanical safety test for EV battery packs under the Indian AIS-156 standard. We'll go through why this test matters, how it's done, what the pass criteria are, and common failures to watch out for. Let's get into it. So, what's the purpose of this test? Simply put, it checks whether the battery pack can survive a sudden mechanical impact without becoming a safety hazard. Think road potholes, emergency braking, or a minor collision. The test simulates those sudden impulse forces and verifies that the battery pack, doesn't leak, catch fire, or explode. Here's the overall flow. We start with pre-test preparation, then installation and setup, then the actual shock cycle, followed by post-test checks and passing criteria, and finally we look at common failures and solutions. We'll also touch on the custom test option at the end. Before we start the test, three things need to be in place. First, the battery SOC must be in the upper 50% of its normal operating range. Most OEMs go with 90% or above. Second, ambient temperature should be 20 degrees Celsius plus or minus 10. And third, all protection devices, BMS, fuses, isolation monitoring, must be active. A pre-test charge-discharge cycle is optional since AIS-156 is mainly a safety test. For setup, you can test the full battery pack or just the safety-critical subsystems including cells and connections. If subsystems are used, you need to demonstrate they represent the full pack's safety behavior. The BMS or ECU can be left out if it's not part of the main casing. One important point, the battery must be mounted only through its original OEM mounting points on a rigid fixture. No extra clamping. This ensures the shock loads go through the pack exactly as they would in the vehicle. Now the actual test. AIS-156. Annex 8D uses a half-sine shock pulse. It's the standard waveform for simulating impact loads. The parameters depend on the mass of the battery. For packs under 12 kilograms, 150 grams peak acceleration, 6 millisecond pulse duration. For packs 12 kilograms and above, which is most EV traction packs, 500 meters per second squared, roughly 51 G, with an 11 millisecond pulse duration. The battery gets 3 shocks in the positive direction and 3 in the negative direction for each of the 3 axes, X, Y, and Z. That gives you 18 shocks in total. This makes sure the pack is tested from every direction. Higher acceleration or longer pulse duration can be requested by the manufacturer if needed. On the left, you can see the half-sine pulse profile. The peak and the 11 millisecond duration are clearly marked. On the right is the actual shock test execution on a battery pack using a shock machine. This kind of documentation is important for test reports and post-test analysis. After all 18 shocks, the battery must be inspected. As per AIS-156, it passes if none of these are observed: electrolyte leakage, rupture for high-voltage packs, fire or explosion. Leakage is checked visually without opening the pack. For high-voltage packs, there's an extra requirement. Insulation resistance must be at least 100 ohms per volt after the test, measured as per Annex 5B. Beyond the mandatory criteria, we also recommend checking for casing cracks or deformation, connector and bus bar loosening, any cell displacement inside the pack, and BMS functionality. These aren't legally required but are critical for real-world reliability. After the shock test, a standard charge-discharge cycle as per Annex 8, Appendix 1 needs to be done unless the BMS prevents it. This is basically a functional health check to confirm the battery still works correctly after the stress. The test ends with a 1-hour observation period at ambient temperature, watching for any delayed leakage or thermal events. Let's look at what typically fails and how to fix it. Connector and terminal loosening is very common. The fix is locking fasteners, correct torque, and flexible bus bars. Casing cracks happen when the enclosure can't handle the G-force, use thicker walls or impact-resistant aluminum alloy. Cell movement inside the pack can cause internal shorts. Foam padding and better clamping structures help. A drop in insulation resistance points to wire damage or internal displacement. Use abrasion sleeves and maintain proper clearances. And BMS or sensor failures from PCB cracks are solved with automotive-grade connectors and conformal coating. If any failure is found, do a root cause analysis, fix the design, and repeat the test. So, can you customize the mechanical shock test under AIS-156? The answer is yes, but only to a limited extent, and only with test agency approval. You can increase the peak acceleration, use a longer pulse duration, or even use a different pulse shape if you can justify it technically. For example, if an OEM has real road impact data from their specific vehicle and wants to test at a higher shock level, that's allowed with agency agreement. But what you cannot change, the total number of shocks stays at 18, and all 3 axes must be tested. Those are non-negotiable. At November Services, we provide full AIS-156 mechanical shock testing using pneumatic and electrodynamic shock machines. We handle everything: fixture design, test execution across all 3 axes, instrumentation, agency coordination with ARAI, ICAT, and NABL labs, and detailed failure analysis with design improvement recommendations. If you're working on AIS-156 compliance for your battery pack, feel free to reach out. Link is in the description. That's it for the mechanical shock test. Thanks for watching. If you found this useful, do like and subscribe. We'll see you in the next one.